Hi friends, in today's class we are going to learn singular value decomposition, in which we are going to see definition, existence of a singular value decomposition, some applications and problems based on SVD. Okay, now let's first see what is a singular value decomposition of a matrix. So consider a matrix A of order m cross n. So then singular value decomposition of A is a decomposition of a matrix into a product of special matrices. What are that special matrices? Let's see. Or even we can call it as a factorization of the matrix of A into special matrices. So A can be decomposed as U sigma into V transpose. So where U is a unitary matrix, it's a unitary matrix. V is also a unitary matrix. U is a unitary matrix, that means U into U conjugate transpose is identity, and V is a unitary matrix, that means V into conjugate transpose of V is equals to identity is also equals to V conjugate transpose of V. Okay, and sigma is a rectangular diagonal matrix, is a rectangular diagonal matrix. Okay, with non negative real numbers on the diagonal, with non-negative real numbers on the diagonal Okay, so basically sigma has a structure of this form: sigma 1, these are the diagonal entries, sigma 2, okay, it's a sigma r. So here U is a unitary matrix of order m cross m. Okay, V is a unitary matrix of order n cross n. So sigma is a rectangular diagonal matrix of order m cross n. Okay, so here this is a matrix of order m cross n. So here there will be some zeros, depends on the order and the rank of the matrix, and here there are zeros. Okay, so where sigma i's are greater than 0. Okay, they are real numbers and positive. So these sigma i's are called singular values. Okay, these sigma i's are called singular values. Even we can restrict these sigma i's in the order sigma 1 greater than equals to sigma 2 greater than equals to sigma r. Okay, we can obtain such a singular value decomposition of a matrix A. So now if we talk about the existence of a singular value decomposition of a matrix A, so any matrix A over C can be, over C means over the complex number, can be decomposed as a U sigma V transpose. Okay, where U is a unitary matrix of order m cross n, V is a unitary matrix of order V n cross n, and sigma is a rectangular diagonal matrix of order m cross n. So now let's talk about applications of singular value decomposition. So the first one is to calculate pseudo inverse of a matrix. As we know that we talk about the inverse of a matrix is only when the matrix is a square matrix. Okay, so by using singular value decomposition, we can calculate inverse of a matrix even if it is not a square, even when its determinant is 0. For example, like we have a, if we consider a matrix A with entries 1 0 0 1 0 1, so then its a pseudo inverse is 1 0 0 half 1 half. Okay, one can check that A pseudo inverse into A, this is equals to a 2 cross 2 identity matrix. So basically this is called as a left pseudo inverse of a matrix A. Second, It is used in image processing. Basically, this matrix singular value decomposition is used for the image compression. Third, it is used in digital signal processing. Fourth, it is used in the principal component analysis. Basically, when you have a data, if you want to identify which component is very important or which vector, along which vector the data is very important, you can use singular value decomposition to identify that. It is used in the low rank matrix approximation. Suppose you have a matrix A of a high rank and you want to approximate that with a low rank matrix. So you can do that by using singular value decomposition. And when we say talk about approximation, we require a norm. So with respect to the Frobenius norm, we can approximate a matrix by using singular value decomposition. So now the question arises, how to find singular value decomposition of a matrix? So now let's consider a matrix of order m cross n. Then we know that A into A conjugate transpose and A conjugate transpose into A are Hermitian matrices. Second, eigenvectors of Hermitian matrices or eigenvectors of Hermitian matrix are orthogonal. Okay. So now let's see how to find the unitary matrix V. So V is constructed by using eigenvectors of matrix A conjugate transpose A. Okay, so as we know that when we will find the eigenvectors of A conjugate transpose A, so that eigenvectors are going to be orthogonal. So we will divide that orthogonal vectors by its norm, so it becomes an orthonormal vector, and then we will place that orthonormal vectors column wise to construct V. Okay, similarly U is constructed by finding eigen vectors of matrix A into A conjugate transpose. Okay, so this is how U and V are constructed. Then sigma is constructed, which is a rectangular diagonal matrix. So the singular values, we saw that the singular values are sigma 1, sigma 2, sigma 3 and so on. So these singular values are the square root of the eigenvectors of A conjugate transpose A. Okay, in fact A conjugate transpose A, these two matrices have same set of non-zero eigenvalues. Okay, so these two matrices have same set of non-zero eigenvalues. So once we find the eigenvalues for V, means once we find the eigenvalues of A conjugate transpose A or A conjugate transpose, we take a square root of that. So by that we will get our singular values, and once we get our singular values, we can get our matrix sigma. Okay, so this is a process of finding singular value decomposition. So now let's solve some problems based on this. We are going to cover some different types of problems. So we have some formula to quickly get the singular value decomposition. So once we get the eigenvectors of A conjugate transpose A, means basically once we get our matrix V, we can get our matrix U by using the formula Ui is equals to A into Vi upon sigma I. So by using this formula, after getting V, we can get U quickly. So now we are going to solve some problems of calculating singular value decomposition of a matrix. In that we are going to cover different types of problems, like we will start with the square matrices, then we are going to move to the rectangular matrices. So now let's start with the example 1. So A is a 2 cross 2 matrix with entries 3, 0, 4, 5. So now we are going to find singular value decomposition of this matrix A. So this is a real matrix. So basically the A conjugate transpose is nothing but the A transpose. So A transpose is equals to 3 0 4 5. Okay, so now let's construct. First we are going to construct V, so we are going to consider the matrix A transpose A. So A transpose A turns out to be 25, 20, 20 and 25, and one can see that it's a symmetric matrix. So now let's calculate the eigenvectors of this matrix. So first we need to calculate eigenvalues. So for that we have to calculate characteristic equation. So the characteristic equation for a 2 cross 2 matrix is lambda square minus trace of the matrix. So the trace, which is nothing but diagonal entries addition. So it's a 50 lambda plus its determinant. So determinant is 225 equals to 0. So now let's find root of this equation. So it's a lambda square, it's a quadratic equation. It's a minus 45 lambda minus 5 lambda plus 225 equals to 0. So by solving, by taking common, we easily get that lambda equals to 5 and lambda equals to 45 are the roots. So lambda equals to 45 and lambda equals to 5 are the roots. So these are the eigenvalues of the matrix A transpose A. Okay. So once we get the eigenvalue, we can quickly construct the singular values. So sigma 1 will be the square root of the largest eigenvalue. As we are going to follow an order, we are going to have a sigma 1 greater than equals to sigma 2 greater than equals to sigma 3, like that. So sigma 1 will be square root of 45, okay, and sigma 2 is a square root of 5. Okay, so now as we can see that A, we are representing A as a U sigma V transpose, and U is a 2 cross 2 matrix. It's a square matrix, so U is also a 2 cross 2, sigma is also a 2 cross 2, and V is also a 2 cross 2 matrix. So by this we can quickly construct our sigma matrix. So it's going to be square root of 45 it's a square root of 45 0 0, and here it's going to be square root of 5. So this is our sigma matrix. Okay, so now let's continue this. Let's find the eigenvectors of A transpose A. So for that, let's consider lambda equals to 45. So we are going to consider A transpose A minus lambda I of X equals to 0. We are going to find the solution of this system of linear equations. Okay, A transpose A minus lambda equals to 0, and we are taking lambda equals to 45. So we can quickly see that we get minus 20, 20. Here also it's a 20 and it's a minus 20. And then we can take it as an column vector x1, x2. This is equals to 0, 0. Okay. So now we get, it's very easy to see that we are getting an equation minus x1 plus x2 equals to 0. So that is nothing but x1 equals to x2. So we can get our first eigenvector capital X1 as an x1 is x2, and here is also x2. So this is equals to x2 times 1 1. Okay, so we can take our first eigenvector. Let's say we are finding v, so let's say v1, small v1. This is our eigenvector 1 1. But as I said, we are going to find the, once we find the eigenvector, we are going to normalize it. So the norm of vector 1 1 is nothing but square root of 2. So let's divide by square root of 2. Okay, so now we have v1. So similarly, we are going to solve for lambda equals to 5. We are going to solve for lambda equals to 5. So consider A transpose A minus 5i into x equals to 0. Okay, so here we get matrix as 20, 20, 20 and 20 into x1, x2. This is equals to 0, 0. So then the equation is x1 plus x2 equals to 0. So x1 is minus x2. So if we consider our vector x2 as an x1, x2, so what we are getting is minus x2 x2. So this is equals to x2 times minus 1 1. So we can take our vector v2 as vector minus 1 1, but again we are going to normalize it. So the norm of this vector is square root of 2, so let's divide by square root of 2. Okay, so now we have our matrix. So now we have our matrix V. Now we have our matrix V. So our V matrix is V1, which is 1 by square root of 2, 1 by square root of 2, and then V2, which is minus 1 by square root of 2 and 1 by square root of 2. Okay, so we got the matrix sigma, we got the matrix V. So now we have to find matrix U. So for that, one can consider matrix A transpose, calculate its eigenvalues and eigenvectors, and similarly normalize it and place it column wise to construct the matrix U. Or we can use a formula which I stated above to get the vectors Ui by using Vi. Okay, and the formula was Ui is equals to AVi upon sigma I. So let's take I equals to 1. So we have U1 equals to A matrix. So the A matrix is 3 0 4 5. Okay, then Vi, which is V1. So V1 is 1 by square root of 2 into 1 by square root of 2 upon sigma I, which is sigma 1, so which is square root of 45. Okay, so now this is equals to, what we get is 1 by square root of 45 is nothing but 3 square root of 5. Then here product turns out to be 3 by square root of 2 upon 9 by square root of 2. So what we are getting is 1 by square root of 10 into 1 vector 1 3. Okay, so we got u1. So now let's calculate u2. So u2 will be equals to, again it's a 3045, and then minus 1 by square root of 2, 1 by square root of 2 upon sigma 2, which is square root of 5. Okay, so now this is equals to, again you keep it 1 by, you can give 1 by square root of 5 outside, and then the product, which is a, so this is minus 3 by square root of 2, and then it's a minus 4 plus 5, it's a 1 by square root of 2. So this is equals to 1 by square root of 10 into vector minus 3 1. Okay, so as you can clearly see that u1 and u2 are orthogonal vector, as well as their norm is 1. So we can quickly get our matrix U. So what is our U matrix? As we can take 1 by square root of 10 outside, and then we have 1 3 minus 3 1. Okay, so this is our matrix U. So now let's consider example 2, which is the matrix A equals to 0 2 0 0. Okay, so then A transpose is equals to 0 2 0 0. Okay, so now let's calculate A transpose A. This is equals to 0 0 0 4, and then it's very clear that eigenvalues, since it's a diagonal matrix, so the eigenvalues are diagonal entries, so the eigenvalues are 4 and 0. So then what is our sigma 1, which is a square root of 4, which is equals to 2. Okay, so while calculating sigma is are the singular values, and they are non-zero positive values. Okay, so don't consider this 0, don't write it sigma 2 is a 0, only consider the positive values. Okay, so 4, so sigma 1 is square root of 4, which is 2. So then quickly we have our sigma. Again, it's going to be a 2 cross 2 matrix, so it's going to be 2 0 0 0. Okay, so now let's further calculate eigenvectors of A transpose A. So let's first consider lambda equals to 4. So consider lambda equals to 4. So then A transpose A minus lambda I, so it's a 4i equals to into x equals to 0. So this matrix is minus 4 0 0 0 into x, which is x1 x2, this is equals to 0 0. Okay, so then what we are getting from here, we are getting x1 is equals to 0. So then if we consider our matrix vector x1, the eigenvector, so it's a x1 x2, so x1 is 0, x1 is 0, and we have x2 here. So then this is equals to x2 times 0 1. So now what we can do, we can take our vector v1, which is the first column of vector v, which is the first column of matrix v. So we have v1 is equals to 0 1. Okay, this vector norm is already 1, so we don't have to divide with this norm. So now let's consider another eigenvalue, which is lambda equals to 0, and then again we consider A transpose A minus lambda I, which is lambda is 0, so it's a 0 into x equals to 0. So then what we get? We get 0 0 0 4 into x, which is x1 x2, this is equals to 0 0. Okay, so then what we get? We get 4x2 is equals to 0. So we get, this implies that x2 is equals to 0. So by similar calculation, we get our eigenvector x2 as x1 x2 is 0. So it's an x1 times 1 0. Okay, so we can take our v2 to be a vector 1 0. So then again it's a normal vector, it's a norm is 1 already. So then what is our matrix v? We are getting our matrix v as an it's a 0 1, the first column, and the second column is 1 0. Okay, so this is our matrix v. So now by using v, let's consider u, because we have already calculated sigma. So now let's find the matrix u. So now for calculating u, we are going to use the formula ui is equals to a vi upon sigma I. Okay, so now this is equals to, what is A matrix? Our A matrix is 0 2 0 0. Okay, we are taking I equals to 1. So okay, let's write the generalized formula for it, the sigma vi sigma I. Okay, so here we just have 1. Sigma I takes the value 1 because we just have a sigma 1, and as a non-zero eigenvalue, so we already got sigma 1 as 2, and all the other diagonal entries are 0. So for 1, we will get u1 is equals to 0 2 0 0, and then v1 we got it as a 0 1 upon, it's a sigma 1 is 2. So now this is equals to, we get it as 2 0. Okay, and we have a 1 by 2, so we are getting u1 as a 1 0. So this is our u1. So now the question is how to calculate u2, because we doesn't have any other singular value. We doesn't have a sigma 2. So you can take u2 can be taken as any orthogonal vector to u1, and with a norm 1. Okay, so it's very easy to see, if we u1 is already have 1 0, we can take u2 as a 0 1. It's orthogonal to 1 0, and the norm of u2 is also 1. So by this we get our matrix u as a column vectors 1 0 0 1. Okay, which is an identity matrix. So now let's consider u sigma v transpose. So U is 1001, sigma is 2000, V transpose is 0110 transpose. Okay. So now by this product turns out to be 0200. Okay. So this is our matrix A. So now let's consider an example where A is not a square matrix. So consider A is equals to 3 1 1 minus 1 3 1. Okay. So now now let's find singular value decomposition of this matrix A. So A transpose is equals to 3 1 1 minus 1 3 1. Okay. So now let's calculate matrix V first. So for that we are going to consider matrix A transpose A. So matrix A transpose A turns out to be, it's going to be a 3 cross 3 matrix. It's a 10 0 2, then 0 10 4 and 2 4 2. Okay, this is our A transpose A matrix. So now let's calculate eigen values of this matrix. So the eigen values of this matrix is lambda equals to 12, 10 and 0. One can use the formula lambda cube minus trace of above matrix lambda square plus sum of principal minors of the above matrix minus determinant of the above matrix equals to 0 to calculate the eigenvalues. So by that form, then by solving that characteristic equation, we get lambda equals to 12, 10 and 0 as the eigenvalues. So then quickly we get sigma 1 as square root of 12, sigma 2 as square root of 10. Okay, so then as we have A, as we are decomposing A as a product of U sigma V transpose. So A is a matrix of order 2 cross 3. Okay, so U is going to be a matrix of order 2 cross 2, sigma is going to be of order 2 cross 3, and V is going to be of order 3 cross 3. So then we have our sigma matrix is equals to, it's a 2 rows 3 columns, so it's a square root of 12, square root of 10, then 0 0 0 and here also 0. So this is our sigma matrix. Okay, so now let's calculate eigenvectors of A transpose A. So now let's first consider lambda equals to 12. Okay, so then A transpose A minus 12i of x equals to 0. So then this matrix turns out to be minus 2 0 2 0 minus 2 4 2 4 minus 10 into x1 x2 x3. This is equals to 0 0 and 0. Okay, so now we get two equations from here. Let's consider minus x1, the first row equation, minus x1 plus x3 is equals to 0, and then we can consider the second row, which is minus x2 plus 2x3 is equals to 0. Okay, so then we can apply Cramer's rule to get the solution. So by applying Cramer's rule, we get x1 upon determinant of 0 1 minus 1 2 is equals to minus x2 upon determinant of minus 1 1 0 2 is equals to x3 upon determinant of minus 1 0 0 minus 1. Okay, so then we get x1 upon 1 is equals to minus, or we can take it and directly simplify, x2 upon 2 is equals to x3 upon 1. So then we can take our vector v1. Okay, so vector v1 as a 1 2 1, and then we can divide by its norm, which is 1 upon square root of 6. Okay, so after this let's consider the eigenvalue 10. So we are going to consider A transpose A minus 10i of x equals to 0. Okay, so then what we are going to get our matrix as? We are going to get our matrix as 0 0 0 2, then 0 0 4 2 4 minus 8 into x1 x2 x3 is equals to 0 0 0. Okay, so by solving, what we get from the first row, the equation we are getting is an x3 is equals to 0. From the second, again we are getting x3 is equals to 0. From the third, we are getting x1 plus 2x2, then it's a minus 8x3, but it's already 0. x3 is 0, so we get this is equals to 0. So we get x1 equals to minus 2x2. So then we can write our vector x as a x1 x2 x3. This is equals to x1 is minus 2x2, then x2, and then 0. So we are getting vector as x2 times minus 2 1 0. Okay, so then we take our v2 as minus 2 1 0, and we divide by its norm, which is 1 upon square root of 5. Okay, its norm is square root of 5, so we divide by its norm. So then we got v1 v2, and now last v3 is remaining by considering eigenvalue 0. So now let's consider lambda equals to 0. So what we get? Consider lambda equals to 0. So then A transpose A of x, okay, lambda is 0, is equals to 0. So then what is the matrix that we are getting? We are getting, actually it's going to be the same matrix. It's 10 0 2 0 10 4. Okay, then 2 4 2. This into x1 x2 x3. This is equals to 0 0 0. Okay, so now the equation that we are getting is 10x1 plus 2x3 from the first row. This is equals to 0, and then from the second row we are getting 10x2 plus 4x3. This is equals to 0. Okay, so that is nothing but we can just cancel the common factor 2, and the new set of equations that we are getting is 5x1 plus x3 is equals to 0, and 5x2 plus 2x3 is equals to 0. So again we can apply Cramer's rule. So by Cramer's rule, what we get? We get x1 upon determinant of 0 1 5 2. Okay, this is equals to minus x2 upon determinant of 5 1 0 2 is equals to x3 upon determinant of 5 0 0 5. Okay, so by this, by solving further, we get x1 upon minus 5 equals to x2 upon minus 10 is equals to x3 upon 25. Okay, so minus 10. So then what we are getting, our vector v3? Our vector v3, we can actually cancel the common factors here, which is we can cancel 5. So we have minus 1, minus 2, and then 5. Okay, and then we have to divide by its norm. So 1 upon square root of 30. Okay, so we got our vector v1, v2, and v3. So now basically we got our matrix V. So now V is a 3 cross 3 matrix. We got all the 3 column vectors. Now we are going to construct U by using V. So but for U it's a 2 cross 2 matrix. Okay, so we just have to use sigma 1 and sigma 2 to get the value of U by using V. Okay, so now let's start by using formula. So remember that U is a 2 cross 2 matrix. So 2 cross 2 unitary matrix. So now, so formula is ui is equals to avi upon sigma I. Okay, so then what is going to be u1? u1 is a v1 upon sigma 1. So this is equals to a matrix. A matrix is 3 1 1 minus 1 3 1. This multiplied with v1. So v1 matrix, v1 vector is 1 2 1 into 1 upon square root of 6. We can take it here. Okay, this divided by sigma 1. So what is our sigma 1? It's a square root of 12. Okay, by simplifying, what we get our u1 is, we get u1 as 1 upon square root of 2 1 1. Okay, this is the value of u1. Similarly, we can calculate u2 by using the formula a v2 upon sigma 2. Okay, so this is equals to you can just quickly simplify by putting v2. What we get u2 is 1 upon square root of 2 vector minus 1 1. Okay, so by using this u1 and u2 we can construct our matrix u. So what is our u matrix? It's a 1 upon square root of 2 bracket 1 1 minus 1 1. Okay, so now we got the matrix u, v and sigma, and one can check quickly that a u into sigma into v transpose, this is the matrix A. Thank you so much.